2.7 practice problems. Which of the following complete Lewis diagrams represents a model containing a bond angle that is closest to 120 degrees? So when we are looking for bond angles that is closest to 120 degrees, we are going to remember all of our possible structures and look for bond angles of 120 degrees approximately. So we have that option here for the seesaw, for the partial, for the trigonal bipyramidal, and also for bent and trigonal planar. So we are going to be looking for anything that is going to have that shape. So as I go through all of these, this is going to be linear. Linear is going to have a 180 degrees bond, so that's not going to be it. Next up, I have a tetrahedral, which is going to have a bond angle of 109. So that can't be it. Then I have an H3, which is going to be trigonal pyramidal, and that's going to be 109 again. And then we have this very long thing here, but we are looking at this central atom here. We have 3 bonds, no lone pairs. And that is going to be trigonal planar. Again, we are looking at this main central atom. We have 3 bonds, no lone pairs, so that's trigonal planar, so that is 120 degrees. So D would be my choice. For question number 2, it says Lewis diagrams of molecules of 3 different hydrocarbons are shown above. Which of the following claims about molecules is best supported by the diagrams? All atoms in molecule 1 lie in one plane. That means that everything is going to be straight, flat out. This is not going to happen with single bonds. We are going to create a that's one more carbon than we need. We are going to be creating this angled structure here. The hydrogens are going to arrange themselves around so that they are away from each other. They are not going to lie within one plane. All molecules have the same empirical formula. That is also not going to be correct. They do all have the same number of carbons, but they do have different number of hydrogens, so that can't be true. The carbon-to-carbon-to-carbon bond angle for molecule 2 is close to 180 degrees. This would mean that everything would be linear. This central carbon has 3 things coming off, no lone pairs. So that would be trigonal planar, which is 120 degrees, not 180. Leaving me with the strongest carbon-to-carbon bond occurs in molecule 3. I know that this is also correct because I have a triple bond here. Triple bonds are stronger than double bonds, which are stronger than single bonds. So that all checks out. So D would be my answer choice. Number 3, in the following diagrams, elements are represented by X and Z, which form molecular compounds with one another. Which diagram represents a molecule that has a bent molecular geometry? So I am going to need more than one thing coming off of the central atom, so A is immediately eliminated because I can't be bent if there's only one thing coming off. My bent options here, I can either have 2 bonds, 1 lone pair, or 2 bonds, 2 lone pairs. So this has 2 bonds and 2 lone pairs, so this is looking good. This has 2 bonds, no lone pairs. That's going to be linear. This has 2 bonds, no lone pairs. That is also linear. So B is going to be my choice since I have 2 bonds and 2 lone pairs. The geometry for the SO3 molecule is best described as, so SO3 is going to be something like this. It is a resonance structure, so we are fluctuating between who has that double bond. So we have like that 1.5 bond situation going on here. But we have 3 bonds, no lone pairs. So 0 lone pairs, steric number 3, that is going to be trigonal planar as my answer choice. Lewis dot diagrams for carbon dioxide and sulfur dioxide are given above. The molecular geometry and polarity of the two substances are. So when I look at these two, this has 2 bonds, no lone pairs. This has 2 bonds, 1 lone pair. This is going to be linear. This is going to be bent. And for polarity here, this is going to require a resonance structure where we have that like 1.5 bond situation going on here, rather than a true 1 to 2 bond, and we do have a lone pair. Since we are bent and we have a lone pair, we are also going to be polar versus the carbon dioxide, which is going to be non-polar. So I will look for something that is going to have something along that line there. For the molecular geometry and polarity, they are going to be the same because the molecular formulas are similar. This is actively not true. They have different shapes and they have opposite polarities. The same because carbon and sulfur have similar electronegativity values. They actively don't have similar electronegativity values. Different because the lone pairs of electrons on the sulfur atom make it the negative end of the dipole. No, lone pairs alone don't make it the negative portion of the dipole. We are looking for something that is more electronegative, not just that we have lone pairs, period. And then finally, different because sulfur has a greater number of electron domains, regions of electron density, surrounding it than carbon does. Carbon has a steric number of 2. We just have 1, 2 things coming off of it, whereas sulfur has a steric number of 3, 1, 2, 3, 2 bonds, and 1 lone pair. So D is going to be my choice. For question number 6, which of the following Lewis dot diagrams represents the molecule that contains the smallest bond angle? So we are going to be looking for whoever is most restricted, and I'm going to look at all of the types of bonds here. Here we have steric number 4, 4 bonds, 0 lone pairs. That would be tetrahedral, so we are going to have a bond angle of 109. Here we have trigonal pyramid, where we have a steric number of 4, 1 lone pair, 3 bonds. That is also bond angle of 109. Here we have a steric number of 3, 3 bonds, 0 lone pairs. 3 bonds, 0 lone pairs. We have a bond angle of 120. And then here for the linear, we are going to have, or sorry, this is not linear. It's actively not linear. This is going to be bent. This is steric number of 3, 1 lone pair, 2 bonds, and I have a bond angle that is greater than 120. Coming back and fixing something I caught whenever I was stating that the bond angles were going to be greater than 120 here. For the trigonal pyramidal, my bond angle is also going to be greater than 120, greater than 109. Or sorry, less than 109. Okay, the electron configurations are the electron geometry is going to be similar since it is 4, the steric number is 4. However, the lone pair is going to force the bonds to kind of come in closer together than if it was only bonds. So B is going to be my choice because that lone pair is going to kind of squish down the bonds to be kind of closer together than if it was all straight bonds only. The hybridization for the carbon atoms in the molecule represented above can be described as, so we have both of these carbons have single bonds coming off only, and we have 4 things coming off, so that is going to be sp3. Remember, you can add the superscripts for your hybridization to add up. That should be the steric number, the thing that is coming off of your carbons. So 1 plus 3 is 4. This is going to be sp3 hybridized. What is the hybridization of the carbon atoms in the molecule Ethyne represented above? So we have, for both of the carbons, we have a steric number of 2. We have 2 bonding domains coming off. Remember that you can add up the superscripts for your bonding types to see if it matches. We should have it add up to 2. This means that this is going to be sp hybridized. Which of the following molecules contains exactly 3 sigma bonds and 2 pi bonds? So as I draw these out, we have a triple bond here. We have 2 singles, 1 double here. We have 1 triple, 1 single here. And we have 2 doubles here, whereas for the C2H2, we are going to have 2 singles and 1 triple. So as a reminder here, my pi bonds are going to be when the p orbitals are overlapping, and I'm going, and my sigma bonds are when my s orbitals are overlapping. So sigma bonds are going to be from single bonds. So if I don't have any single bonds, I'm going to eliminate those options. Now I need pi bonds. Pi bonds, we need 2 p's overlapping, which means I need at least a double bond present, potentially higher, and then at least 1 single bond present. This is only going to account for 1 pi bond, not 2 pi bonds. So that's eliminated. This only accounts for either one sigma bond and 2 pi bonds, or 2 sigma and 1 pi, so that's not going to work. This, on the other hand, we have the single bonds, which are definitely sigma, 1, 2, and then 2 pi, 1, 2, 3 is going to exist for the C2H2. Of the following molecules, which has the largest dipole moment? So we are looking for the greatest electronegativity difference between my molecules. So anything where I am bonded with myself, my electronegativity difference is 0, so that's definitely not going to happen. Following it up with looking at who I have present. So I have carbon monoxide, carbon dioxide, which is a notably non-polar compound. This is extremely non-polar compound, so that's definitely not going to have a large dipole moment. So I am really just looking for the electronegativity difference between hydrogen and fluorine, or carbon and oxygen. Noting that the electronegativity is highest in the upper right-hand corner, fluorine is going to have my highest electronegativity, and hydrogen has an electronegativity that is pretty close to that of carbon. The distance between hydrogen and fluorine is greater than that of carbon and oxygen, so I am going to predict that the hydrogen-fluorine bond is going to be the most polar and therefore have the largest dipole moment. Which of the following molecules has a pyramidal shape? So pyramidal shapes we have two options here. We have trigonal pyramidal and we have a trigonal bipyramidal. For the trigonal pyramidal, we need a lone pair and 3 things coming off of the central atom. For the trigonal bipyramidal, we need a steric number of 5 0 lone pairs. So, looking at everything here, I need to have at least 4 elements coming off of are in the actual molecular formula, because I have to have 3 things coming off of my central atom. So these are eliminated immediately because I just don't have enough of everybody. Then comparing between these two, the NH3 is going to win since it has that lone pair, which is required for a pyramidal shape, whereas the BH3 is planar. There is no lone pair there, so NH3 is going to be my answer choice. Which of the following molecules contains polar covalent bonds but is a non-polar molecule? So we are looking for something that is going to be non-polar in terms of if it is symmetrical, but the actual bond electronegativity differences do have a high electronegativity difference, which would lead us to think that it would be polar. But because of the symmetry, it's going to be non-polar. So nitrogen is eliminated immediately because I'm not going to be polar if I am bonded with myself. Ammonia is historically just known as a polar molecule. Again, we have not the largest electronegativity difference between nitrogen and hydrogen in the first place, but since we are not symmetrical and we end up with a pyramidal shape, we are polar, so that is not going to be the case. This, I'm going to have a pretty large polar moment here since one of my bonds is going to be with chlorine, whereas the other 3 are with hydrogen. This is very much not symmetrical, so that's not going to work out. And this one also is not going to work out symmetrically. So that also is going to be polar. Whereas this, the carbon to chlorine electronegativity differential is pretty large. However, since all of the chlorines have the same electronegativity difference, we don't have a dipole moment going on because they are all equally pulling on the electrons from that carbon. Next up, we have: which of the following arranges the molecules nitrogen, oxygen, fluorine in order of their bond enthalpies from least to greatest? So this is going to be, bond enthalpies are going to be how much energy I have to put in order to break the bonds. And you'll notice here, these are all diatomics. However, the fluorine to fluorine is a single bond, the oxygen to oxygen is a double, and the nitrogen to nitrogen is a triple. And that is the order of least amount of energy to break to most. I have to break 1 bond versus 2 versus 3. And so my answer choice is going to be A, since that goes single, double, triple bonds. Pi bonding occurs in each of the following species except. Pi bonding requires a double bond or more to be present. This is going to have single bonds only between carbon and hydrogen, so this is going to be my answer choice. Which of the following molecules has the shortest bond length? I am going to look for whatever is going to have the greatest number of bonds in between those things. Remember that triple bonds are my shortest bond. The nitrogen-nitrogen is a triple. Oxygen to oxygen is a double. Chlorine to chlorine is a single. Bromine to bromine is also a single. And iodine to iodine is also a single. So the nitrogen-nitrogen bond is going to be my shortest bond because triple bonds are my shortest bonds. According to the VSEPR model, the progressive decrease in the bond angles in the series of molecules CH4, NH3, H2O is best accounted for by, this is, remember you were dealing with bonds versus lone pairs. So for CH3 versus CH4 versus NH3 versus H2O, the lone pairs are going to exert more of a force and force the actual bonds to be closer together than if there were just other bonds present. So my decreasing angle between my bonds is going to be specifically because of the increasing number of unshared electrons, the increasing amount of lone pairs. Which of the following is a nonpolar molecule that contains polar bonds? So we need a nonpolar molecule based off of geometry, but we would suspect a polar compound based off of electronegativity difference. So I'm going to delete anything that is going to immediately be a polar molecule. The geometry is going to be unequal, therefore it is polar. Anything that the electronegativity difference between hydrogen and chlorine is very great. This is going to be a polar compound here. And then NH3 is notably a polar compound because, again, of the because of the molecular geometry of that compound. So between these two, these are my only non-polar compounds. However, the bonds between fluorine and fluorine are non-polar since we have the same electronegativity for both fluorine and fluorine. So my only answer choice is going to be that of carbon dioxide. The electronegativity difference between carbon and oxygen is pretty great. However, this is very symmetrical and therefore is non-polar. Which of the following molecules represented below contains a carbon with an sp2 hybridization? Remember that this 1 plus 2, so I need 3 things coming off of that central carbon. So CH4, that's going to have 4 things coming off. CH2Cl2 is going to have 4 things coming off. C2H6, we'll see what happens. I'll build that out. The C2H2Cl2, we'll build that out to see what happens. And C2H4Cl2, we can also build that out. So with the 2 carbons and 6 hydrogens, I am going to have a steric number of 4, so that cannot be sp2 hybridized. Then for this, I am going to end up with 3 things coming off of my carbon, so steric number of 3, so this is looking good for that being sp2 hybridized. And then finally here we have 4 hydrogens and 2 chlorines. So steric number of 4. So D is my only answer choice. Which of the following has a zero dipole moment? So this means that we are completely non-polar. So I'm going to eliminate anything that is going to be polar at all. So ammonia, again, very notably polar. HCN is also polar here, very, very uneven distribution of electrons there. The sulfur dioxide is also polar, so no. The nitrogen dioxide also notably polar, so no. PF5, we are in an expanded octet, however, we are non-polar because we are very equal in the distribution of those electrons. Which of the following species is not planar? So the things that are planar, we have the trigonal planar, square planar, linear is also planar. Okay, anything where we are going to have a popped up shape is going to be not planar here. So building all of these out, sorry, I reversed that on accident. My apologies. Since the PCl3 has one lone pair and 3 things coming off of it, we are trigonal pyramidal, which means that we are definitely not planar. The BF3 molecule is nonpolar, whereas the NF3 molecule is polar. Which of the following statements accounts for the difference in polarity of the two molecules? So as a reminder, BF3, we are not going to end up with any lone pairs on that central atom, whereas in NH3, we do end up with a lone pair on the central atom. And this pushes it down into a trigonal pyramidal shape, whereas the BF3 is in a trigonal planar shape. So I'm looking for something along those lines. And that is going to be D. Unlike BF3, NF3 has a non-planar geometry due to the unshared pair of electrons of the nitrogen atom, making that a polar molecule.